In this video, I'm just going to be covering some introductory aspects of probabilistic reasoning. We're going to be doing some formal probability here and talking a little bit about um, things related to betting and all that sort of stuff. Just as a disclaimer here, I assume no responsibility or liability for how you use any of the information that is going to be presented in these next few videos. If you take this information and you make some bad sporting bets or bets in a game of poker, I'm not liable for any of those decisions that you actually make. All right. Primarily, we're going to be talking about how to calculate odds as percentages and vice versa, how to calculate the probabilities of compound or complex events from single events, and then we'll also be talking about Bayes' theorem a little bit and what Bayes' theorem is useful for. Okay, now, but when we're talking about probability in a more formal sense, what we need to keep in mind is that there are different ways of using the term probability, and there are different kinds of ways of theorizing about probability. Now, it's also the case, I'm not going to discuss this here, but in areas like concrete mathematics and those kinds of things, there's also a difference between talking about probabilities and talking about likelihoods. And this is also the case in philosophy of science. Probabilities and likelihoods are not the same thing. Now, but for our purposes, we're not going to get into any of that stuff. There's plenty of literature on the differences between what we're talking about when we're talking about probabilities and what we're talking about when we're talking about likelihoods. If you're interested in those kinds of topics, send me an email and I can send you some of the relevant literature on that. Okay, now, but as far as talking about probabilities in certain kinds of ways, all right, the first way is just what we would call the abstract ways of talking about probabilities. Okay, so abstract probabilities are just the chance of any result out of all the possible results. Okay, so for example, the abstract possibility of getting a heads versus a tails in a standard coin flip is 50%. And when I say standard coin flip, I mean not one of those odd situations where you flip a coin and it lands on its side, so then it's neither a head nor a tail. We'll leave those kinds of cases out. Obviously, in real life, if you flip a coin, that could happen. You could end up with the coin somehow, landing in a bowl of Jello or something and getting stuck on its side like that. So then it would be neither be heads nor tails. So by standard coin flip, we just mean we're ruling out those kinds of cases. So in a standard coin flip, the abstract probability of getting a heads versus a tails is 50%. It's either going to be heads or tails. Heads or tails exhaust all the possible options, so it's going to be one or the other. Okay, so when we're talking about probability in this abstract sense, what does that mean? For abstract probabilities, the results are both mutually exclusive, meaning if one happens, it means that the others do not happen. But with abstract probabilities, the results are also mutually exhaustive. So what's the difference here? So if two results are mutually exclusive, that means the occurrence of one means that the other one doesn't happen. But mutually exclusive does not mean mutually exhaustive. Okay, so my being in Illinois right now is mutually exclusive with my being in Florida right now. So if you know I'm in Illinois right now, you automatically know I'm not in Florida right now. So those are mutually exclusive, but they're not mutually exhaustive. Why? They're not mutually exhaustive because there are other options available. Now, but when we're talking about the abstract probabilities, we are exhausting all the possible options that there are. So abstractly, all of these results are both mutually exclusive, meaning if one occurs, the others do not occur. The occurrence of one eliminates the other ones from possibly occurring. And they're mutually exhaustive, meaning we account for all of the relevant possibilities here. Okay, so more formally, what this means is for any given set of possible results A, B, and C, if A, B, and C exhaust all the possible results, then the chance of either A occurring or B occurring or C occurring is equal to 1. So when you've got a set of mutually exclusive and mutually exhaustive results, that means one of them must occur, and whichever one occurs means that the other ones must not occur. So if given our case here, A, B, and C, so if A, B, and C are mutually exclusive and mutually exhaustive, then the chance of either A happening or B happening or C happening is going to equal 1. All of the individual probability of A happening, the individual probability of B happening, and the individual probability of C happening on their own, without being conditioned on anything else. When you add all of those individual probabilities up, so the initial probability of A, the initial probability of B, the initial probability of C, those will add up to 1. So the chance of either one of them happening for a set of mutually exclusive and mutually exhaustive results is equal to 100%, or 1 if you're representing it as a decimal. Okay, now, but when we're actually doing empirical studies and statistics and things like that, we usually don't talk about probabilities abstractly. Most of the times we use a relative frequentist interpretation of probability. Okay, so what is relative frequency? Well, relative frequency is a ratio of either positive or negative results, and that should say number, not number, of cases in a sample. All right. Okay, so for a standard coin flip, or a normal coin flip, I guess I said here, you have a 50-50 chance of your guess being correct. It's either going to be heads or tails in a normal or standard coin flip. So you've got a 50-50 chance of being correct abstractly. Okay, now, but if I want to ask what the chances are of you being correct in a series of coin flips, right? So suppose I'm going to flip a coin 10 times in a row, and I'm going to ask you to guess heads or tails each time. Okay, now, so what that means is that all of your picks are independent events. So each individual coin flip is an independent event of every other coin flip. So if I want to ask, okay, what are the chances of you being correct X number of times out of Y number of coin flips? Do we have good reason to think that you would be correct 50% of the time in a series of coin flips, given that each individual coin flip is an independent event? No. So, I mean, to make that kind of prediction would be a lot more complex than just looking at all of the abstract possibilities per se. Why? Because it's the number of times being correct in a series. Okay. Now, likewise, if I want to talk about the likelihood of you getting some kind of disease, if I say, well, based on your medical history, you've got a 13% chance of contracting this disease. Is that 13% taken from just all of the abstract possibilities, or is it taken from a representative sample, right? So sampling, anytime we talk about sampling and whether samples are representative, and we talk about how we can make claims about a target group based on knowledge of the sample, we're not talking about abstract results or abstract possibilities here. We are using a relative frequentist interpretation. Now, but there is also a subjectivist interpretation of probability. It's also called a personalist interpretation of probability. Okay, now what a subjectivist says is that what probabilities express are our degrees of credence that we give to a given result happening. Okay, so what we do is we make predictions, and we have certain degrees of confidence concerning whether or not those predictions will come to pass. All right, now, so in what kinds of cases does this occur? All right, well, this occurs in um, a lot of times in cases of valuation for publicly traded companies. All right, so if I have X number of shares, publicly traded shares available in my company, and I'm going to set a given price for those shares, what am I doing? That price is usually set by my confidence that my company will do well. Well, I could be wrong about that, right? Okay. In cases of betting, and so suppose you and I are playing poker, okay, and here's what happens. Um, so you know you've been betting small, so let's say that the blind is 20 cents, and uh, you know you call, and then we see the flop, we see the first three cards, you bet 20 cents. The turn card comes out again, you bet 20 cents, everybody else folds, and I say stay in. I see your 20 cents. All right, the river comes out, you bet 20 cents again. So I know that you're betting pretty safely. I mean, given the fact that you're not raising the bet through any new round of betting, you're not going above what the blind is for each round of betting. I take that as an indication that you're not too confident in the hand that you have. You're not too confident in your cards. Why? Because you're not willing to take a risk to lose a large amount of money or a large amount of your chips, right? So what are my options? Okay, so I can either, so you bet 20 cents on the river again. I can either see your bet, I'll see your bet. I'll bet 20 cents as well. Um, and then, we turn our cards and we see who the winner is. Now, that would be a safe bet, right? Because that would also mean that I don't stand to lose much as well. Now, but if I believe that the reason why you're betting so safely is because you don't have a lot of confidence in your own hand, what will I do? I might go in with a heavier bet. So if you bet 20 on the river, I'm going to see your 20 and I'm going to raise you 60. So I'm going to be a little more aggressive. Now, what does that mean? That means that I have a higher degree of confidence in the hand that I have, or at the very least, I have reason to believe that you have very low confidence in the hand that you have, right? Now, do you see why I'm not basing this decision per se by actually collecting data and comparing the number of positive cases or negative cases to the total number of cases, right? I'm basing my decision on how to bet on several different factors. But the confidence that I have that I'm going to win, or my confidence in this case that my interpretation of your actions is correct. I mean, depending on how well I know you, I mean, that will come up in a moment. That will help determine the kind of bet that I'm willing to make. Okay, so here's what I might do. Um, and this is why when it comes to things like poker, knowing who you're playing with is so important. Okay, suppose I just see your bet. All right, I bet 20 cents. I see your 20 cents. We flip our cards, and you had an okay hand. So you win the hand, but it's not like you had a monster hand compared to mine. Okay, well, didn't I learn something about you, right? So what I've noticed here is that there might be a correlation between the confidence that you have in your hand and how you actually bet, right? And I'm gonna log that in my brain for next time. Okay, now, but if you bet 20 and I bet 80 and you immediately fold, I mean that tells me something about initially something about how you're going to play this game, right? Or if I bet 80, you initially bet 20, I raise you 60, and then you see my 60, we turn our cards, and you're like, I got nothing. I know you're not really that good at buying the pot. I mean, if your cards were garbage, what should you have done? You probably should have made a much larger bet earlier on, right? And as people fold, then you take the chips or you take the money, depending on how you're actually playing the game. Okay, but in making that decision, okay, what's the chance of my actually winning? I'm hedging the degree of confidence that I have in my own cards, in the way you bet, the way you play the game, your confidence in your own cards, right? So this is not a like strictly empirical. I have verified data, and that's how I'm making these kinds of decisions. No, so here, the confidence that I have is part of my reasoning of making a determination of the chance that I'm going to win. Okay, now, and if somebody wanted to ask me, okay, well, put a number to the degree of confidence that you have that you are going to win in this scenario. Okay, um, higher than 50%. I mean, so when it comes to subjectivist interpretations of probability, I mean, the numbers that we actually give, as far as, well, I would give it a degree of credence of 8, or I would, something like that. I mean, this is largely arbitrary, but that's fine. So if a credence of, for example, if a credence of 50% would be basically an agnostic position. I mean, I'm not quite sure, but blah, blah, blah. Then positive credence would have to be given a value over 50%. Negative credence would have to be given a value of under 50%, right? Now, but how high over 50 and how low under 50, there's no like objective fact of the matter here that we would use to determine, okay, well, what percentage am I willing to give to my degree of credence here? I mean, a lot of times the numbers are just sort of arbitrarily chosen. I mean, same with I mean, why do we use a scale of 1 to 10 for talking about how bad your pain is? I mean, why? Because how many values are there between 1 and 10? There's an infinite number of values between 1 and 10. So I'm not saying this would be a nice thing to do, but if I were in the hospital and my nurse said, "How's your pain level?" I'd be like, "Pi." Not pie like, the tasty pie, but, pi, 3.14. Let's just terminate it to 3.14. I mean, I'd probably get like an evil stare or something like that. But why? No, no, no. You just use whole numbers from 1 to 10. Well, why not? I want to use pi. My pain level is pi, right? That's what I'm going to use. Okay, well, that's just arbitrarily sort of chosen. So if 10 is worst pain imaginable and 1 is hardly no pain at all, but I mean, we could pick any, if 100 is worst pain imaginable and 1 is no hardly any pain at all, and right, it's arbitrary, and that's fine. Okay, all right. Now, the other concern here is what does it mean for values probabilistically in percentages to actually be statistically relevant? All right, so here we can talk about it in terms of positive correlation and negative correlation. All right, okay, so think about this way for a moment. Suppose we want to talk about the probability that John, that would be me, John will fail to get pregnant given that John has no ovaries. And this is represented formally with, the probability of F, and that the thresher stroke there means given that. So the probability of F, the probability that John will fail to get pregnant, given that John does not have ovaries. John lacks ovaries, which I do. I've never had ovaries. Okay. I'd think that probability would be pretty high, don't you? So the probability that John will fail to get pregnant and that John does not have ovaries, I think that would be a pretty high probability. Okay. Now, but compare it to this. Um, Compare it to the probability that John will fail to get pregnant given that John has no ovaries and John takes Yaz. Aha. So I don't know if they make Yaz anymore, but Yaz was a birth control pill. Okay, so suppose one day, you know, you come to one of the schools I teach at, let's say North Central College. You come to North Central College while I'm in the faculty office, and you have a question, and you just see me sitting there eating my lunch, and then an alarm goes off, and I go, oh, hang on, and I take out my pack of Yaz, and then I open it up, and I take my pill. And I say, I take my pill every day. You can't be too careful. I've already got 3 kids, and I don't want any more, so I'm taking all the precautions necessary to make sure that I don't get pregnant. I don't want to get pregnant. Okay. Now, but here, what's actually going on? So we've got the probability that I will fail to get pregnant given that I have no ovaries, and we're comparing that to the probability that I will fail to get pregnant given that I have no ovaries and I take out, right? Okay, that would look like this. So the probability that John fails to get pregnant given that John has no ovaries and John takes yes. Um, I don't know why, but on Prezi, the ampersand looks weird, but that's an ampersand. Okay, stands for and. So the probability that John will fail to get pregnant, which is the result, given that John does not have ovaries and John takes yes. So the fact that we're adding my taking yes means that we have extra information here. Okay, now but here's the question. What symbol should go between these probabilities? So the probability that I will fail to get pregnant given I have no ovaries, and the probability that I will fail to get pregnant given that I have no ovaries and I yes. What symbol should go between them? Less than, greater than? What do you think? That's right. The symbol that should go between them is equal to, right? The probability that I will fail to get pregnant given that I don't have ovaries is equivalent to the probability that I will fail to get pregnant given that I don't have ovaries and I take yes, right? Okay, now, so this is important. What then does this tell us about Y? Well, that tells us that Y is not statistically relevant to F, right? So if the probability of F given not O is equivalent to the probability of F given not O and Y, I mean, in order for Y to be statistically relevant, then Y would have to change the probability. But Y doesn't change the probability. I mean, so to get technical here, if you formed a hypothesis, John will fail to get pregnant in virtue of the fact that John takes yes. That's your hypothesis. It's John's taking yes, which explains why John fails to get pregnant. I mean, that would be a null hypothesis. The fact that I'm taking yes is not at all causally relevant, or in this case, statistically relevant to the chances of my failing to get pregnant. The chances of my failing to get pregnant, given that I don't have ovaries, is equal. It's equal probable that I will fail to get pregnant given that I don't have ovaries and I'm taking yes. So since the presence of Y does not change the probability whatsoever, that means that Y is not at all statistically relevant to F. Y is not statistically relevant in my failing to get pregnant. Okay. Now, and if we want to talk about evidence here, since you observed me taking yes, this would also be the case. Your observation of seeing me take yes is not evidence that I will fail to get pregnant. So if you come to the faculty office I'm sitting in at North Central College and you see me take a Yaz birth control pill, you do not have evidence that I am going to fail to get pregnant, given that if you already knew that I didn't have ovaries. I mean, that's a qualification here. So if you already know that I don't have ovaries, then you seeing me take Yaz doesn't sort of what we would say compound upon the evidence. It doesn't count as evidence that I'm going to fail to get pregnant. Okay, now, so what does that mean about evidence? Increasing the likelihood of truth, and keep in mind I'm using likelihood here rather loosely. Increasing the likelihood of truth is a necessary condition for a given observation to count as evidence. Okay, so increasing the likelihood of truth is a necessary condition for an observation to count as evidence. So if I know that a given observation does not increase the likelihood of a given result occurring or a given proposition being true, then I know automatically it does not count as evidence in favor of that proposition. Okay. Okay, now, but this is where we might make a mistake. Just because increasing the likelihood of truth is a necessary condition for a given observation to count as evidence, that does not mean it is a sufficient condition. All right. So even if a given observation would increase the likelihood of a given proposition being true, that's a necessary condition for that observation to count as evidence in favor of that proposition. It doesn't follow from that increasing the likelihood of truth on its own is a sufficient condition to count as evidence. Okay, so let me give you an example. All right, so suppose I'm participating in a raffle. All right, so what's the difference between a raffle and a lottery? So with raffles, you purchase a given number of tickets and we keep calling numbers until we find a winner. With lotteries, on the other hand, there may not be a winner. So given the fact that this is a raffle, we have a total number of tickets available for purchase, and we're going to keep picking numbers until we find a winner. So that means, given that it's a raffle, there's a guarantee that there is going to be a winner. There is no such guarantee for a lottery. Okay, so let's suppose there are 1,000 total raffle tickets, let's say at the local high school football game, and I buy 10, and let's say that they're $5 each. All right, so I spend $50, all right, and I have a 1% chance of winning. So if there are 1,000 total raffle tickets, and we're going to keep calling numbers until there's a winner, and I buy 10 of them, I have a 1% chance of winning, given these figures. Okay. Now, but that's predicated on all of the total raffle tickets being purchased, right? So where am I getting that 1%? Well, there's 1,000 total raffle tickets, and I buy 10 of them. So initially, I have a 1% chance of winning. So I buy 10 of the total 1,000. So initially, just based on the raw figures of what's at stake in the raffle, I have a 1% chance of winning, right? However, I find out this later. I find out that not all of the tickets were sold. Only 999 tickets were sold. So if all 1,000 tickets were sold, my chance of winning would be, 1 out of 1,000. But now my chances of winning are 1 out of 999. Why? Because not all the tickets were sold. Okay, so that means my chances of winning have increased. My chances of winning increased to 1.001%. Okay, so we have an increased chance that I am going to win based on the new information that I have available. Okay, but do I have evidence that I'm going to win? No. This it would be absurd for me for my the degree of credence that I have towards the proposition I am going to win the raffle, simply because I know one less ticket was sold than the total number of tickets available for sale. I do not have evidence, and in this case, I mean compelling evidence. I don't have really more reason to think I'm going to win than I did before. I mean, the chances of me losing are still really high, right? Close to 99% chance that I'm going to lose, not win. Okay, so that is why simply knowing that the probability or the chance that you are, that something is the case, that by itself does not count as evidence. Okay, now in here we can make distinctions between what we would call prima facie or initial evidence and then compelling evidence. So you have compelling evidence when your degrees of credence not only ought to change, but really ought to change significantly, right? So if I buy 10 tickets and I find out that only 20 were sold, oh, well, yeah, now I've got a lot better chances of winning here, but I still might not win. Now, and given the fact that only 20 tickets were sold, that's not going to be a really big cash prize, right? So I spent $50 to win $100 if I win at all. I mean, that may not be even worth it in the long run, right? Or if I buy 10 tickets and I find out 11 tickets were sold, I'm in a community where they just don't really participate in raffles. Okay, well, now my chances of winning are 10 out of 11. So yeah, now my chances of winning are really high. But again, I spent $50 to win $55. That may not be worth it in the long run. Okay. All right. So this video is getting a little lengthy, so I'm going to be chopping things up into some bits here. All right. And I will see you all later.